This is the first Quest user to ever be on the event instance, so we had to get that fixed because it's kind of important for my panel. So I'm sure you probably don't know who either of us are. I'm not currently wearing one of my main avatars, but many of you guys might recognize me from the accessories on my public volleys that are pretty much everywhere. I've only been making content for this game and platform for about a year, pretty much since last Furality Aqua. I've gained a lot of random knowledge about the platform, a lot of stupid, not useful stuff in a way, but my assistant Foxy over here is going to be helping me demonstrate some of these things since they aren't really demonstratable with just one person. An important thing to know is that they are currently on a Quest 2, which is why we had the delay, because we had to get the world working for Quest. First important thing is we are going to have this index. This covers everything that we're going to be going over. So at the bottom left, you'll see what current section we're on. And then on the right, you can see all the sections that we're going to be covering through this. It's a variety of different things. There isn't necessarily one specific focus for this, mostly because I couldn't figure out enough stuff to fit for one panel, so I decided to just throw a bunch of different stuff into there. We're going to first go over just some basic tools, some fairly basic stuff with that, and then work our way up in complexity from there. So first up is tools. This is by no means a comprehensive list of what you're going to want to do any of this, but it's kind of a basic list of stuff. I'm going to have links to everything that I am showing in this section at the end of the panel, so you can find the GitHub pages for them and whatnot. The first one here is the Creator Companion. I know this might be a little controversial, since its initial release was a bit controversial, but I do actually really think this is an important tool to learn and start using. Mostly because it simplifies everything for pretty much every single user of this. So as far as end user advantages go, community created repositories essentially allow you to install things like the normal SDK, where you can just bump the version of it to whatever the newest one is released in the program. People can make repositories that do that and release new versions, and all you have to do is go in and manage the project and update it to that. It's really easy as an end user to get the latest packages, and it'll even make sure all the dependencies that are needed are at the right versions, as long as the person setting up the package has done it properly. As a package developer, it's also really nice because you get basically instant versioning for whatever package you're doing, and if you're using GitHub, there's actually actions that you can set up to pretty much do the entire build and release structure for you without having to do any of that in Unity. And it's also, this is another thing that maybe was lost, is that the system is technically VRChat agnostic, so as long as your package doesn't have anything that specifically needs one of the VRChat SDKs, you can actually still import the Unity package that is made into a non-VRChat Unity project, and it'll just work without any issues, which is, I think, something that a lot of people don't realize with the way the system works. Another thing is animator's code. This is somewhat the backbone of most of this panel. You can pretty much automate every single action that you can do in the animator controller editor. So makes doing loops, like you can do loops on an entire set of states and transitions and make extremely complex state machines that just would take forever to make otherwise. The beyond here is actually made out of animator states using a black and white image that it looped over to make that image. So yeah. The next thing here is a few of my own tools. One of these is actually part of what we'll be covering here. which is animator's assembly. So I'll go into that a little bit later. But another nice one that I'm just putting out here if people need it is shader finder. You can essentially drag in the root of one of your avatars and select a certain shader from your project for it to find, and it'll select every game object that has a material with that shader. So if you've ever been uploading a Quest version and you're confused on why it's complaining about a non-compatible Quest shader and you can't find it, that's kind of the solution to that, since it's not in the SDK. So we'll be moving to simple concepts now. I don't want the word simple to make it seem like if you don't know this, you don't know anything, because these are still kind of advanced things, but relative to the rest of the panel, I would consider them simple. So first thing is parameter drivers. Learning these is actually very important if you want to do anything complex. Normally with the animator system, you can't easily directly control parameters other than having animations that drive them, but that is severely limiting for many different reasons, mostly because you can just set them to a number. What the VRChat parameter drivers allow you to do is either A, set a specific parameter to a specific value. You can add a constant number to a parameter. You can also copy the value of one parameter into another, and alongside that you can actually do remapping to change from like one range to another range when it goes to that other value, which is really nice for converting different types of numbers to different parameters. And lastly, you can also do like actual randomness in the animator controller without needing a bunch of weird layers to do that. There's just a parameter driver that sets things to a random value. It even works for Booleans. So this is one of our first semi complex things here. On the right, you're going to see there's this graph, and those are two different integers. So syncing and saving more than 8 bits. What I mean by that is normally when you have in your parameter list saved parameters, they can only go up to 8 bits, which only gives you, if it's an integer, up to 255 numbers that you get access to before you can't save any more than that. So if you want to make anything that's more complex or is a larger number, you got to get a little special with how you're doing it. So the gist of this is every single one of these white like boxed in areas is a different integer that is stored in the parameter list. So you can essentially go through. The basic idea is, let's say you have a number counting up and it gets to 99. If you add one more into that number, it would go to 100. You have a state transition detect that it went to 100, and you then reset that parameter to 0, and then add 1 to your next set of 2 digits. So you're essentially rolling over the 1. You're carrying over the 1 and then setting that integer to 0. And I've actually got a video later that kind of shows this, but you can essentially do clocks. You can do 8-digit counters just natively. It's a very useful system. Another cool thing that you can do is doing actual calculation loops in the animator controller. So everything you're seeing here is one layer, and I'm going to go into these individual sections here. But you can essentially, this one essentially runs a, for lack of a better analog, a heat simulation. So there's an integer that is keeping track of a fake heat value, and that is incremented, I think it's every second I run this loop. That's incremented every second based on various different actions that my avatar is doing. Which I can actually switch into that avatar, because why not? So that gets incremented for every single different action I'm doing. So if I start flying or whatnot, that'll actually add more to that heat value. And then at the start and the end of this loop, there's something that sets a number. There's an integer that keeps track of fan speeds, and it sets that number based on what the heat value is. And at the end, depending on what that heat value, or depending on what that fan number is, it will then subtract a different amount from the heat value every loop. So you can pretty much run full basic simulations in here. One of the important things of this is basically an if statement state setup. So you have a transition coming in from the bottom into what is essentially a dummy state that's just there to branch things. The transition that goes directly up to the exit if statement, that is if the thing you're checking for is false. And then the transition that goes over to the true state is if what you're checking for is true. Those are also instant transitions. And then they end up both meeting back at the exit if statement. And this allows you to, you can also add in a state if you wanted to do something when it's false, but this essentially allows you to do a simple if statement. Now, you can technically merge these. You can merge a bunch of these without needing the 3 state blocks, but the problem is if you want to copy it and expand it, it becomes really annoying because you need way more transitions to do it. But this is already kind of a important thing to understand that you can do is you can do full-on if statements in the animator controller itself to determine what you do. So this is kind of a pseudo-graph for what's actually happening here. So on the left we have the graph that we saw earlier. On the right is a simplified version that very briefly goes over the blocks here. So an important thing to note is that the first thing that it checks is if you are running the animator locally. The reason we want to do that is we don't want this running on everyone's machine because states that do a lot of instant transitions, animator controller layers that do a lot of instant transitions are very expensive as far as frame times, mostly because pretty much every single frame it's doing something. So ideally, if you can, you want it to only run locally. And the way we get around that is all the values that this loop sets are synced parameters. So once our local animator runs them, they just go out to everyone else through the network through the normal parameter syncing instead of having this run on their machine as well. It also means all the numbers are the same for everyone that sees it. So then you enter the start of the loop. We first remove temp based on what fan setting, so 1, 2, or 3. And then we go through all of our if statements in order based on how much to add to the heat. And then we set the fan speed based on the resulting heat value after that. And then we have a single state that waits for a second and then goes all the way back to the start of the loop, which then just continues that again. So being able to do loops like this is really important. I have a video here. Okay, that's playing. On the top left, and this is actually all on the back of the head of this avatar. On the top left, you can see that there's the heat value there that is decreasing. I don't know if the fan value is readable there, but there is a value that shows what fan speed it's currently at. But the heat value is decreasing from that loop that I just showed you. And then a little earlier I showed you the multiple integers. So you can see boops received, that is 1,741. That number's normally too large to be synced, but you can increment that just fine without any issues. I don't know why the video stopped playing, unless that was the full time. But and another thing you'll notice is below that system clock. That, since that's a synced set of parameters, that is how long I have worn the avatar without resetting it, which would reset the saved parameters. And you'll see here, as that number approaches 59 and then one more gets added to it, it will roll over. So you can see it went to 262600. So that's kind of a demonstration of how that rolls over. It pretty much just adds one to the thing to the left of it and then sets itself to 0. And that's just running every second. It's just adding one. There we go. So this is a warning to... I don't want this to forewarn you guys from experimenting with this, but you have to understand that everything else I'm going to cover in this panel is... I wouldn't say abusable per se, but if you don't think about the ramifications of the way you set things up, it can have some pretty bad performance implications. So I just want to lay that out here, just so everyone is aware with that. So now we're going to talk about advanced Physbone systems. So this is some complex, I would say, new tech that no one else has experimented with yet. So the goal of this section is to essentially recreate Unity's built-in constraint system for the most part in its entirety. So anyone that's developed on PC and has kind of gone into the advanced part of avatar development probably knows what constraints are. You can move stuff around to different positions than what's in the hierarchy. You can do parent constraints, musician constraints, move things to the world origin. That's what the section is about, is recreating that. The other goal is getting this to function on Quest. That is kind of the idea for everything here. Everything you've seen so far and everything you will see going forward works completely on Quest. Some of it isn't as performant as I'd like, but it does still function on Quest the way it's set up. Third point is to be viable for actual avatars, so nothing like all 8 Physbone components need to be used and all the transforms are maxed out and everything like that. It has to be viable to actually be used. Honestly, easy to tweak. I don't want to have a setup script that kind of interprets the values if you're using it at the end. You want to be able to kind of understand what you're looking at when you're looking at the Physbone inspector. So this section is going to be a little abstract, mostly because if I was to try and cover, like if I was to try and do this as a tutorial, I would probably be here for 2 hours explaining the way this works. So I'm going to kind of cover the abstract way of it works, and if you want to ask me later specifics on how to set these up, you're more than welcome to do that. First, I gotta quickly talk about the VRC devs semi-ruining my month here. Halfway through me working on this panel and working on the tech demos, the VRC devs released the Squishbones update for Physbones, which meant I now had to go through and redo pretty much all of the tech demos I had already started working on to use the new methods, since Squishbones kind of changed the game as far as how viable a lot of these are going to be. So that was fun. I have been pretty much working nonstop since Squishbones came out, getting tech demos done and getting this panel done. I literally earlier today was finalizing things like 2 hours before this panel. So it's been kind of tight. So the first one here is going to be Physbone Springs. A lot of these are going to have V1 and V2 in the title of the slides. V1 is pre-Squishbones. So that's how you had to do it before, because we didn't have the ability to do Squishbones. Physbone Springs, pretty self-explanatory. You want a spring effect where you move the transform of one thing and the end of it is delayed from following it. So you can see the blue text, that is the hierarchy of the game objects here. It's not entirely that important, but if you ever want to try and recreate these, it's at least somewhat of a reference. The 2 capsules here, the top one is like the initial state of just being idle when you first load whatever you have this on. The bottom one is if you were to move to the left, it kind of shows the full bone makeup, where all the bones are, basically. So you can see when the capsule moves to the left, the endpoint hasn't moved at all. So the general gist of how this works, and I'm not going to go into it too much because this is the old way of doing it. I don't recommend using this method anymore. But it's essentially you're faking a spring by doing a zigzag, and you have a set pull, so all of those bones want to return to that zigzag, but they won't do it immediately. So that's kind of how that one works. The V2 version of this is way simpler, purely because we have stretch. So now you only need 3 game objects to do this with. The first one just has a Physbone component, and the second one solves the position. The third one is just so you can have something without having to always adjust the ignore transforms. So this one, you literally just have a single bone, and you turn the stretch motion to 1. You set the max stretch to whatever large number you want, as long as it's large enough to reasonably fit in the world. And for good measure, you turn the squish all the way up. What this does is essentially, when you move, the bone itself is now stretching because you've turned it on to have motion affect the stretch. I'm sure a lot of people could try this. I don't even know if there's much to cover else with this one, but This was kind of what spurred on me changing all the other tech demos to represent this kind of stuff. So the next one is doing a position constraint. This is something that wasn't possible feasibly really at all pre-Squishbones. So this one's a little weird to explain, but position constraint, essentially you can say, let's say I have something on my hand and I want to move it to my other hand. Traditionally, the way most people would do that is you just have two copies of the object, one on this hand, and then you just have a toggle that turns on this one instead. What you can do instead is use this and have only one copy of it on the main hand, and you're able to set a Physbone collider on the target that you want it to go to with inside bounds and 0 radius, and when you turn that collider on, the object will move over to where that collider is. So that's kind of the gist of what a Physbone position constraint is. It's pretty much how the position constraints work. But you can have multiple targets that change to different locations that you want, pretty much as the SDK will let you upload with. So you can see there's two XYZ component markers here. One of them labeled target, and then another one labeled, I think it's position or something like that, Physbone. The Physbone is going to the target position with a set offset, and you can see as we go from the one capsule to the other, it follows with that same offset completely. And they are not under each other's hierarchy. The position constraint here is at the root of the avatar. So it's not parroted in any way. The next one here is the V1 version of a world constraint. This one's a little more complicated to explain, but basically you take the spring constraint, and instead of having any pull on it, you actually make it have pretty much 0 on everything. And what that does is when you move, it doesn't actually try and move any of the other Physbones other than to make them connect. So if you have enough of them, what ends up happening is the very end bone doesn't end up moving at all because it doesn't have a reason to. None of the other bones are pulling on it. Main issue is with this, there's actually a maximum distance with this, since you need to set an amount of bones. If you go past the total distance of those bones from the world constraint, it'll start following you, and I can actually demonstrate this one. Let me find it in my huge list of avatars. So if I switch into this, the red here is my player, and the blue is the actual will constraint, like solved position. So if I just start moving around here, it's going to take work pretty well. And of course, the distance I want. Okay, so if I start moving now, it starts moving as well, which isn't what a world constraint should be doing. What is essentially happening is there is now just a snake between my avatar and that world constraint that's just sitting there and not allowing any more movement. So that's kind of the limitation with that one. But now that we have stretch bones, we can essentially get an unlimited distance world constraint. So this one, I also won't go over this one much because I'm actually running tight on the time already because I probably talked about stuff more than I should have, but you essentially have two bones. One goes out to, there's a really weird thing where if you have multi-child type to average, it'll solve the position of those two childs, but it won't do anything to the rotation. So you can essentially lock the axis. And this one allows you to go as far as you want from where you initially place it, and it'll stay in that position. The main limitation with this is there is roll issues. If you go along one of the axes, it'll start rolling. I haven't been able to resolve that yet. I'm sure it's fixable, but I literally just made that in like the past month, so I haven't had much time to experiment with it. Another cool one you could do now as well, and you could kind of do this before, but I think it's better now. You could do a look-at constraint. So you can have essentially a Physbone hierarchy that tries to look at a collider target. So you can essentially track things on your avatar, which is really nice if you want to have followers or whatnot that have things that look at your avatar but also can move around on their own. Now, there's two different ways to do an origin constraint. The simple one is actually kind of a weird Unity quirk. If you make a prefab and then have that prefab in your assets like project folder, if you have either a contact sender, receiver, or a collider on your avatar, and you drag in the prefab from, not from the scene that you're in, but from the project folder itself, it will properly set into the root transform of those components. However, since those components won't exist in any scene, when it tries to load them, that transform gets set to what is essentially just a default uninitialized transform, which just so happens to be always 0, 0, 0. So whenever this tries to place the components at a transform, they will always end up at the world origin. Which is extremely cool as it is. There is a few limitations with this, however. The thing that you want to do has to have the root transform field, so you don't get an arbitrary hierarchy of being able to have like multiple objects and particle systems and whatnot. It's pretty much just the contact senders, receivers, and colliders that you can do this simple version with. However, I've also managed to develop an advanced version of the origin constraint, which I'm not showing as much here because there's a few Physbone components that are needed to make this work. However, what this does is essentially place a inside bounds collider at the world origin, use the position constraint that we saw earlier to get a transform at that position, which means we now have a transform at the world origin. We have a look at constraint to make sure that we're always essentially having that object look along an axis, no matter what axis we're facing or however we spawned it in. And then there's lastly a Physbone with max gravity to make sure it's always pointing down, because if you don't do that, you end up with some weird roll issues. So this allows you to place any arbitrary hierarchy at the world origin, which will become important for the other parts of this panel coming up here. So what are some practical applications of this? Because I'm sure a lot of you are probably wondering this. One of them actually is doing followers that are Quest compatible, which is the thing that many of you guys probably don't know you can do now. This here is my hologram volley, and you can see I have a drone following me behind there. That drone is using all of the techniques I've shown here. This is actually using the V1 of a lot of the techniques. And you can see on the slides as well, I have the Physbone overlay open on this now. So it kind of shows you got to make up a lot of stuff to do this. But I can move around just fine, and this thing will follow me pretty much like any other normal follower will. And this is even using the look at constraint if you would like to put your hand in front of the beam. This is using the look at constraint to determine that beam to face me, and then there's a Physbone collider and receiver that determine how much of that bone is inside of my body, and that controls the emissions. I'm seeing almost no one doing stuff like this, and I'm hoping as kind of part of this panel is to show that you can do this and have people experiment with this. Another good technique is you can actually do cross-avatar data transmission using the origin constraints, which we will get to in a second because it kind of has some wild implications. So this next section, we're going to move away from that for a bit. We're going to talk about Turing complete avatar controllers, which I'm sure a lot of you probably already know what Turing completeness is. And I'm going to switch out of this just so you guys can see me because it's a little trippy. But Turing completeness is essentially the ability for pretty much a device or a system to emulate a Turing machine, which in all intents and purposes, the original Turing machine was essentially you have a set and you can move along a bunch of cards and program in any arbitrary movement of those cards. It's pretty much the starter of what you need in order to determine if you can, I don't know, for instance, run Doom on something. If it's Turing complete, there is likely some way that you could run Doom on the device, even if for many other reasons, it might not be feasible, but in theory, you could run Doom on something that is Turing complete.
Machine.
The image I have here actually is someone demonstrated the fact that Microsoft PowerPoint is Turing complete, and you can run a full Turing machine in a PowerPoint, which is kind of wild. But if anyone sees where this is going, I've basically been able to move this into VRChat. So
no.
I went ahead and designed semi-fake language, mostly because trying to copy from any of the existing languages would cause all kind of weird things. So this is just kind of an overview of this language. It's based around assembly, but with a few tweaks to just make it more readable, since I don't really have a lot of the limits of assembly when it comes to a compiler or whatnot. Here's more of the opcodes. These are the main opcodes that you can do. There's quite a few of them. So, the compiler for this is around 3,000 lines of C#, all in Unity. It has full support for doing things like subroutines, which are essentially functions. It has a full stack that you can interact with. It has go-to commands, and you can do full comparisons on multiple parameters. It has access to the random number generator that we covered earlier with the Physbones. And you can do basic math in it as well. So you can add, subtract, multiply, or divide two different numbers. And there's even rudimentary GPU commands for a screen system that I have implemented. What I have essentially managed to create here is a full-on compiler that can take in any arbitrary any arbitrary assembly code and compile that into an animator controller that can run at runtime in VRChat. So you can see here I pull up the inspector. At the bottom you have an IDE that you can program the actual program that you want to run on the avatar. There's a bunch of different options that you can configure as well, turning the stack on and off, if you want to organize the animator controller graph or not, and then if you want to generate a screen and the pixel size of that screen. The screen allows you to directly pretty much bitmap everything. Like it's a bitmap screen, so you can individually address every single individual pixel on it. Now there's a few drawbacks with this, unfortunately. And there's ways around them, but I have for a few of the drawbacks, I'd have to refactor all 3,000 lines of that C# code, and I haven't done that yet, for hopefully obvious reasons. So the main one here is large enough animator controllers could actually visually freeze the client for a few seconds. My main guess on why this happens is because the amount of parameters generated on the animator is quite a lot. We're talking 200 plus for pretty much anything that you can imagine being on an animator controller. And something with the way VRChat loops through that when it unpacks the world makes it really unperformant. At least initially, but once you load the avatar, it's actually fairly well running. You have slow calculation times. This is mostly due to the fact that each CPU step essentially is a frame. So if you want to do multiple steps for a CPU instruction, it's pretty much how many frames are you taking up, and that adds up fast when it comes to time. And many of the instructions need to work across multiple CPU steps due to the limitations of I can't do operations directly, like the parameter drivers, you can't do them on two parameters at the same time. You can't directly add one parameter to another. So to get around that, I essentially have to loop over both parameters and essentially add the one into the other progressively, which is very slow. Another issue is every value is in the form of an int, which is kind of my mistake when I started coding this. But that also means if you try and do any binary operations, you need to convert it to binary first, which is really slow again because I have to do things over multiple steps just for one instruction. The solution to that is rewrite all of it to use bools and do it in binary, but I have to rewrite all of it, and that would take forever. This has been already like a 3-month project that I've worked on this compiler for. I'm going to show you a video here real quick. this is in Unity. You can see I have an avatar up there that has the system on it, and at the bottom I have the animator controller. This shows that if you have the layer trying to render, the Unity editor itself slows down to about 5-10 frames per second, just trying to redraw the animator controller window, since there's so many different components in there. And you can see it jumping around. Many states or many opcodes have a lot of states that are needed to make them up due to a lot of the workarounds that I have to do.
So that's what that is.
I think we gotta wait for this one to finish. I don't remember how long it is, but yeah, it's quite intense to try and preview this stuff in the Unity editor. It actually compiles slower as well if you have that window selected, because every time it tries to modify the animator controller, the animator window tries to redraw that modification, making it extremely slow. But I'm waiting for this video to finish here. There we go. So this is kind of overview of just what a basic program looks like. So you have your instructions on the left. Your variables usually start with a $sign. Those are registers, and then you can do constants for different things. Or like for example, if you have a divide, it takes in 2 registers, and the 3rd register is where it outputs to. And you can even do things like comments, which I've shown here. Now, when we compile this to the animator controller, this is a very short and small snippet of what that looks like. The animator controller in Unity actually does not allow me to zoom out enough to get the entire thing. So you can see every single line, so every single column, that is an individual line. And then as you go down in that column, those are all of the states needed to make up that single instruction. So a lot of them are simple ones where it's just copy the parameter from one to another. But things like multiply and divide and addition have a lot of states, and you can see those are the ones that go off the screen, because those ones have to do an essentially expanded version of those calculation loops I showed earlier, except way more complicated and automatically generated, because that's how I'm using this. There's not really another way around doing it like that. Please make sure
you are muted.
So this is this slide's kind of important. The stream may appear frozen for about 2 to 5 seconds. I guarantee you the stream should not have crashed, but due to the way and what I mentioned earlier, where upon loading these avatars, Unity does not like unpacking them. Specifically, VRChat, Unity does not like unpacking the asset bundles for them. The game will freeze doing that, but it won't actually crash. Now, my client actually takes longer to unpack them than everyone else viewing it, so I'm probably going to not be speaking or be frozen for longer than you see me like load into the avatar. So just keep that in mind if stuff starts running. That's why I'm not talking, because my client is taking longer to load it than otherwise. So let me find it in here.
So, we got any favorite movies?
The timing on that.
Oh, never mind. Just kidding.
So, I loaded the avatar. I don't know if you noticed, people were moving before I was. For some reason, and I don't know why, but the local client runs this worse than the remote clients. I wish I could give you a specific answer. My only guess is that when it unpacks the avatar, it loops through every single parameter on the avatar to try and link it to a synced parameter, or see if it should do anything else with it. And since these generate a crap ton of parameters to do what they do with the screens and whatnot, it gets pretty bad at unpacking it. So you can see on this one, and it is just starting to run for me, by the way. If I move back to this slide, in order at the top, you will see the 3 numbers are loaded in. So we have 365, 432, and then a divisor, which is 4. And then the 4th line is the result of doing the add command. the next line is a result of doing the subtract command, and I actually realized I did a mistake in this assembly code. The subtract command that is represented here is the second number minus the first number. The next line is a result of doing the division, and then under that is the remainder from that division, which is 0 in this case, since there's no remainder when you do that division. And then the very bottom one is the output of doing the multiplication. And I'm going to realize I'm going to move away so people can actually see it. If the camera wants to focus on the text. Because I'm not sure how much of it was captured, but so this, and I'm going to try and stay out of this one for a short while because the screen, the screen parameters, the amount there is here and the size that I've made the screen actually make it lag quite a bit, and since every single one is addressable, they're actually all individual meshes. So it doesn't run that well with this many pixels in this resolution. But you can see all of these numbers are properly calculated if you want to do the math yourself. I'm going to switch out of this so I get my frames back. So that is also that. Oh, yep. All right. I'm close to the end here. So, the next thing here is doing serial transmission across avatars. You can do a max of 16 Physbone contacts on Quest. So if you want to do two-way communication, you have 7 bits to send and 7 bits to receive, and then you need a bit per clock and send or receive. Yes, I know there's smarter ways you can do this by integrating the clock in there, but it makes things significantly more complicated on the animator. If you want to do one-way communication, you can send up to 15 bits in parallel, and then you just need a bit for the clock sending and receiving. Real quickly, this is what the source code for that looks like. This is the sender, and this is the receiver. We are going to switch into them here. I don't know if you have
is it my turn?
Saved, but yeah. I can switch into it and then have you clone it. I don't know if you have it saved. I didn't think about that, but let me find my. Where is it?
Is this right?
No. I need the. You need to clone this one. All right. Face towards. Yeah.
By a little
so
bit.
What you're gonna see, my avatar is gonna start printing things above me. Make sure you just face forward, yeah, so they can see the text. My avatar is printing stuff above me. That is going to be transmitted to their avatar on their end using a serial transmission algorithm. And you can see, so at the bottom is the binary. We need to use 1 and 4 instead of 0 and 1 because the zeros get truncated. And 4 is used because of weird floating point imprecision things when you have a number this large. Above that is the integer version of that number that is being transmitted. And above that is the ASCII character code that relates to that number. So we're able to fully interpret ASCII character codes and print those to the screen. So you'll see here in a second, it all runs locally, so it might take a little bit longer for the stream, so I want to make sure they get it. But their avatar should now be refreshing its screen with that new information that it just received. Seems like mine's not even running on the stream, possibly, so maybe there's something weird going on there. But it's working on my end. I don't know why it's not working on the cam bots, but that's fine. The basic idea is here, right? You can see that they have the receiver text, and that if it was working, they would be receiving things, and that would be redrawing itself. So there's that. So that kind of shows, like, it's very much in an infantile state right now. And you can switch out of it if you want. I would just switch into the Quest audio link one because we'll be getting that here real quick. That kind of shows the infantile state it's in right now. I'm working on improving its performance, but it's iffy. Just because there's a lot of things I have to consider when I implement things. So this last section here is going to be on Quest compatible audio link. I'm actually really tight on the time, and the video for this is actually going to be longer than the time I have left, unfortunately. But the essential gist here is We have a screen space shader that writes data on top of the desktop view, and I'm going to switch into the avatar I need here real quick. We have a screen space shader that writes data on top of the desktop view of my local machine. And I don't know if it's possible to turn the rain off or not. If you could do that, that would be great. Use a Python app to monitor the screen of VRChat and then extract that data from it. Convert that data to a 0 to 1 float, and then push that data back into VRChat using OSC. And doing that, it now means it's in the animator controller itself instead of inside of the shader. And we can use that to drive various different animations. And using the origin constraint method before, we can place contact senders and receivers at the world origin and offset them from each other to transmit integer values. And then on the Quest avatars, we just use contact receivers to get that data back out, and we can drive animations directly from it, which is why I wanted the Quest user here. So if I move here, this is kind of a graph that goes over that. So VRChat to the shader, out to a Python script viewing the screen. That sends it back through OSC, that goes in the animator, back into VRChat, and then the Quest user receives that through their animator controller and can drive animations with it. So now I'm going to play a video that has audio link on it. If the stream cuts off early, I just want you to let everyone know now that there is going to be a Discord channel on the Furality Discord for this. I'm going to try and set up a instance for everyone to join. Sorry, what? Oh, okay. Yeah, so there'll be a Discord channel for that, since this video is longer than the 1.5 minutes I have. So, but hopefully this works. It should, but...
World that's left in a love that's gone silent. Can't look further ways 'cause we're just so blinded. Tell me to hear when I ask you to
if you want to keep it on the cam bots, by the way, I can load up and show the shader. It should show up on the cam bots, I believe. Yep. So if you look to the right of your screen, and sorry for anyone in VR, this is it's gonna be a little annoying, but if you look on the right of the stream, you can see that is the data that my Python script is pulling. So there's able tags being used to locate it, and then each one of those blocks is the individual data that my Python script is grabbing. I'm gonna tweak that. Kind of a jam session at the end here, but feel bad for going over all the time, but so I will mention there's something weird with the audio link here. I don't know what it is. I don't know if it's shader post-processing stuff being weird on my end. It's a bit more reactive than this on a normal audio link world, but I didn't have really a way to test it entirely here yet and tweak it as much as I would have liked, but here's what it is. I think this gets the point across. If I had more time, I would do the entire song, but I can demonstrate this later to people if they would like. But we can fade it out or cut it or whatever if you want. I think this gets the point across at least. It works. The Quest user is seeing it just fine as well. So yeah. If you want to transition to the last slide here. Is it on the last slide? No, it's still playing that. So yeah, thank you for seeing this panel. There's the resource links, by the way. You can find a lot of the stuff on GitHub. So I don't know if I've been cut off or not, but if you want those, there they are. Sorry about how rushed this panel was a little bit, but very tight on time and a lot I wanted to cover, and I didn't even get to go in as depth as in depth as I wanted to. But so just a recap on that. I'm going to be trying to set up an instance through the Furality Discord. There is a channel there specifically for this panel. I'm going to try and get an instance link set up that everyone can join into, because I think it's just easier to talk about it in an instance. But if you want to ask questions there as well, I'll try and answer as many of them as I can about any of these systems, since I really want to get this out there. So, yeah, I've been Hyper133 and lovely assistant here, Foxy. Thanks for watching my panel. Nothing else to say.
Goodbye.